But what actually defines a robot? Well, really, a robot is just a type of automated machine that can execute specific tasks with little to no human intervention. And they do this with both speed and precision. So this week, I actually looked into a lab group who thought, where in that definition does it actually say that the building blocks need to be traditional materials? What if the building blocks were actually cells? And so that is how we got the world's first living, self-replicating, and reconfigurable robotic organisms, and they're called Xenobots. And so even though these are alive, let's think about designing them in the same way we would a traditional machine or robot. And so when we design things, we usually have a function that we want it to achieve in mind. And then in pursuit of that function, we get to choose both the composition and the structure. So here, the researchers knew that they wanted to mess around with cells as the composition, but for the functions, they decided they wanted to see if they could make locomotive robots, robots that could manipulate objects, transport objects, and kind of work together for collective swarm behavior. And so with those functions in mind, they realized, probably just like one cell type wasn't going to cut it. They decided that they wanted to have both a passive cell type, one that provided more of structure, and an active cell type that would allow for some of this motion to occur. So let's look a little closer at how we actually get those building blocks. So what they did was take African clawed frog embryos. And African clawed frogs, their scientific name is actually Xenopus laevis. So you can see Xenopus, that's where they got the name Xenobot from. And so if we look at the development of the African clawed frog, starts off, as we all know, with fertilization, and then you get that first cell cleavage. So one cell becomes two, and then two becomes four, and so on and so on and so on. And eventually you reach the stage called the blastula. And this is when tissue organization kind of first begins. So you get this segregation of different tissue types that will eventually form different parts of your body. So this top part is the ectoderm, and that forms the skin. And then you have the mesoderm and the endoderm, and those form internal portions of the body. And the scientists decided that the ectoderm here would be a good passive cell type to use to create their robots. So they harvested the ectoderm from blastula phase embryos. And then they decided that for their active cell type, they actually wanted contractile motion to kind of act as an actuator for movement. So they took stem cells from this 4-cell stage, and they injected them with mRNA to turn them into cardiomyocytes, so muscle cells, which can spontaneously contract. And that is what they used to allow for motion. So then with these two building blocks, they then got to decide, what does our structure look like in order to get these different functions? And for each individual function was create an evolutionary algorithm. So they fed the building blocks and the end goal into this evolutionary algorithm, which basically creates a random library of designs that are made out of those building blocks and achieve the goal. So they tested that library in a physics simulator, test in simulation, in order to see if they would achieve the function in silico. Essentially, they had this workspace. So there's this bounding volume that they were looking at. And within that volume, they had individual voxels, which is like a 3D pixel. And each voxel is like a chunk of tissue. So it's not a voxel to cell ratio, it's a chunk of tissue. And for each voxel, the evolutionary algorithm could decide, okay, I want this one to be cardiac, I want this one to be ectoderm, or I want this one to be empty space. And so that means that you can get a design library that is 3 to the n different design options. And so from that library, then they would test them in their physics simulator and end up with performative designs. But that's still a lot of designs, and you want to make sure that, it's probably going to work before you try to build them, because it's a lot of effort to create these living robots. So they also fed them through 2 other filters, the robustness filter and the build filter. So the robustness filter is actually just imposing noise into the physics simulation environment. And that noise is meant to simulate some of the unpredictability that can happen in vivo. So they only let designs pass through that could handle that noise and still perform the function that they were hoping to get out of that robot. And then the build filter actually provides the physical restraints to the designs. So the way that they build these, what they do is take layers of tissue. And so you could have like a layer of ectoderm, and then a layer of cardiac, and then a layer of ectoderm, or another layer of cardiac, but essentially layering all of these tissues together. And because they're alive, when you layer them, if you give them some time, they'll actually heal together and create this brick that you can then carve out whatever shape you've determined on your program. So say you end up with something like this. You have your different layers still, and it's 3-dimensional, and that's your robot. But obviously this carving and layering technique limits what designs can actually be built. So you can't have like random voxels of a different tissue type within a layer. So passing it through that filter allowed them to come up with manufacturable designs. Manufacturable and robust designs. And those designs, they actually went ahead and built. And so they called that their realizability generator. Because they realize the designs in real life. You can basically just think of that as building them in vivo. And then with their newly built robots, so our realized designs, they then compared their functionality and their structure to what they expected from their in silico predictions. So that they called their transferability filter. And let's take a little look at what that actually entailed. So the way that they determined whether they did a good job with their little surgery carving technique was to use the Hausdorff distance. And bear with me because this is a bit of linear algebra, but basically they knew what their in silico design was supposed to look like, right? So if they wanted to get something that looked like this, we'll say, so that's their in silico design. But their in vivo carving of it ended up looking something like this instead. The Hausdorff distance is the measure of the greatest of all distances from a point on one set to a point closest in the other set. So if we think of our in silico design, the surface of it being a set of points, and we'll call that set of points A. And the in vivo design, the set of points that make up that, we'll call that set B. We want to know which point in A is closest to a point in B. So if this is the point we're looking at in B, then the closest point to it in A is probably right here, right? So for every point, we determine that. So you can go around each point and determine that. And then of all of those distances, because those are all lengths, we want to know what the longest one is. So the maximum. And that is the Hausdorff distance from B to A. And then you can do it vice versa from A to B. So for each point in B, find the closest point A within set A and vice versa. And then you find the maximum length of those. So the fancy math way to write that is DH equals the maximum, as I just said, so the greatest length. And then it's the supremum of point A in A, and the infimum of point B in B within the metric space AB, and then just the opposite. So supremum point B in B, infimum point A in A, within that metric space. And that just looks really complicated, but just go back to that initial definition, the greatest of all distances from a point in one set to a point that is closest in the other set, where your sets are all the points that make up the in silico design and all the points that make up the in vivo design. And so they use that metric to help them decide what designs were built well and functioned well. So you're probably wondering, like, how did these robots perform? So they actually found that they could move. So that was cool. They could transport objects. So in order to do that, they actually made designs with like little donut shapes. So they had pouches. They could manipulate objects. So actually what they did here was put their little robots into a tank with a bunch of particles, and they found that the robots actually clustered those particles together in little piles. So they just made like little groups of particles. So they were able to manipulate those objects. And they actually, if you put multiple robots in, work together to do that. And in a more recent paper, they actually, instead of putting particles in this dish, they made those particles into stem cells. And so when those stem cells get pushed together in these little clusters, those clusters then form new Xenobots. So this is what they're calling kinematic self-replication, which is unlike anything that nature's evolved organisms do, but these designed organisms are able to do that, which is fascinating and a little scary if you ask me. But an important thing to note to like minimize that fear is that these robots have a self-limiting lifespan. So they can survive about 10 days without nutrients, which is kind of crazy if you think about it, but also kind of nice. So they're not gonna, go take over the world or anything, even though they can self-replicate. And some other cool features about them, though, are that they're entirely made out of cells. So they're biodegradable robots, and they can easily be made biocompatible robots if instead of making them out of frog cells, you make them out of the patient's own cells. And in some more recent work, they also did some genetic manipulation. So you can think about how that might be useful too. You could have different receptors on their surface so they could act as sensors really easily. The other thing that's kind of cool is because they're made out of living cells, they're able to self-heal. So like a traditional robot, you cut off its arm, it's not coming back. You got to fix that. But with these, you can just like slice them down the middle and they just heal right up and keep on doing their thing. Which you can see how all of these things together would make them really interesting for a lot of different possible uses.